Today we're going to be working through exercise 5.3 where we differentiate exponential functions. So this is from your jacplus textbook, of course, and it's the worked examples. So before I start them, I just wanted to point out to you why e is its own derivative. And what I mean by that is when you have y equals e to the x, well then dy over dx also equals e to the x. And I'll just draw a little bit of a picture here of e to the x, and it looks like this. And then, well, if I want to draw the gradient function, well, let's think about what happens. So this is still x, and now we're talking about the gradient. Oops, dy over dx, not dy over dy. So think about if you were walking along this curve and you're going in this direction. So as you go towards negative infinity, so just say negative infinity was over here, you're going to approach a point where you are walking on a flat surface. So in other words, your gradient is approaching zero. So just say we get to negative infinity, which we don't, but just pretend we do, we would be at zero here. And you can see that if you walk the other way, well, you would be going up the hill more and more on a large gradient. So we would get higher and higher, and the gradient is getting steeper and steeper. So as you go towards positive infinity, well, the gradient's going to get larger and larger, as do the y values. And as you go towards negative infinity, the y values get closer and closer to zero, and the gradient gets flatter and flatter, so also closer and closer to zero. So we never do reach negative infinity. So the point is that, well, you would have it like this. So you can see that e to the x is its own derivative. And I should actually say e to the x is its own derivative, not just e. So let's now go to the examples, and keeping in mind that e to the x is its own derivative. So for the first one, I'm going to do it with the chain rule, and I know that you wouldn't have covered the chain rule in Year 12 jacplus yet, but it is covered in Year 11, and hopefully you remember it a little bit. I will show you with the chain rule just so you understand how it works. Then we will just use the rules in order to do the remaining three. So here we've got y equals e to the negative half x. And if we're going to use the chain rule, we would say let u equal neg half x. And u will be whatever is in the power. So therefore we've got y equals e to the u. Now, if we have y equals e to the u, we can say, well, the chain rule is dy over dx equals dy over du times du over dx. And, well, we need each of these constituent parts. So I'm going to start with dy over du, and there's dy, and with respect to u, so we always read it, the derivative of y with respect to u. So what goes in the numerator, the derivative of y with respect to u. And now we can say, well, e to the x is its own derivative, so e to the u is its own derivative. So that's going to be e to the u. There's dy over du. Now we have du over dx. So that's the derivative of u with respect to x. So we expect to see u on the left and x on the right. Derivative of u with respect to x. So that's going to be negative half. Because, you know, 1 times negative half is negative half, x to the power of 0 is 1, so we end up with negative half. And, well, now we can say dy over dx, which equals dy over du times du over dx. So we're just multiplying these two together. So it's negative half e to the u, and of course u is negative half x. So this would be our answer. This is the derivative. And what you'll notice is that the derivative of the power comes out the front. So you don't need to do the chain rule every time, and in fact you shouldn't do the chain rule every time. It's a bit of a waste of time, but that's why it works. So here is our derivative, and we've got that because of the chain rule, but we can always just take the derivative of the power out the front, and that's what I'm going to do for the remaining three. So let's do part B, and part B is y equals 1/4 e to the 2x plus e to the x squared. So this has got two parts that we need to differentiate, and I'm just going to, as I said, do it the short way and say, well, the derivative of 2x is 2 times 1/4 e to the 2x, and then it's going to be plus the derivative of x squared is 2x times e to the x squared, and that means I'm going to get half. 2 times 1/4 is half, e to the 2x, and then we've got plus 2x e to the x squared. And people don't like this where you've got the 2x e to the x squared. It looks kind of messy maybe, but it's correct, so just leave it as it is. So that's our answer. Let's go to the next one, and I might just scroll down. Right, part C. Y equals, I'm going to make this one line as we always do, or sorry, not one line. I'm going to break the fraction down, so it's e to the 2x over e to the 2x plus 3 e to the x over e to the 2x minus 1 over e to the 2x. So e to the 2x over e to the 2x, that's 1 plus 3 x to the 1, x to the 1 minus 2x there, 1x minus 2x is going to be negative x, and then this is going to be minus e to the neg 2x. So now I'm going to just derive it as per usual, so dy over dx equals, well, 1, that's x to the power of 0, 0 times 1 is 0 times x to the neg 1, well, it's going to be 0, that's why that will go. The derivative of negative x is negative 1, so we get negative 1 times 3e to the neg x, and then we've got negative 2 times negative e to the neg 2x, and that will become negative 3e to the neg x plus 2e to the neg 2x. And of course you can put this with positive powers, so dy dx equals neg 3 over e to the x plus 2 over e to the 2x. And this would be the nicest form of the answer, like this. So let's do the last one. So we've got d, which is y equals e to the x minus 2 squared. And we want to expand that, so you can FOIL it if you want to, but really it would be nicest to know that a minus b squared is a squared minus 2ab plus b squared. So you can quickly get it expanded. E to the x squared is e to the 2x minus 2 times e to the x times 2 is negative 4 e to the x. And 2 squared is 4. So now we can just derive it in the usual way. 2e to the 2x minus 4e to the x, and of course the 4 will disappear because there's no x there. So that one actually is quite an easy one, but you just had to know to expand those brackets there. And really by now you want to be using the identities, not having to FOIL things all the time. So that's the basics of the derivative of e to the x. Let's see how they can be applied in tangents and perpendicular lines. So now we're going to determine the gradient of the tangent to the curve with the equation y equals e to the neg x at the point where x equals 1. So you don't need to draw a picture of this, but I'm just going to point out what it is that we're looking at. So there's some equation y equals e to the neg x, and well, that's going to be some curve, and it doesn't matter how you draw the curve. The question doesn't ask us to draw it. But the point is we've got a point where x equals 1, and what we want to know is the gradient of the tangent at that point. I'm just going to draw a different shape because I want to be able to show that a little better. So just say there's x is 1, and what we're looking for is the gradient of the line or the tangent at that point. So obviously my curve is not e to the negative x here, but the point is I want to just point out what the tangent is. So this is the tangent to the curve at the point where x equals 1, and what we want to know is what is the gradient. And again, I stress that this curve that looks more like a parabola, it doesn't look like that. It's just representative of a curve and the tangent which is to the curve at the point where x equals 1. So we're looking for the gradient, so we're going to need a gradient function. So step 1, gradient function. So, well, dy over dx equals negative e to the neg x, and then, well, we want to know when x equals 1. So we're just going to sub in a 1 into that. So dy over d1 is negative e to the negative 1, so that equals negative 1 over e. And that would be our gradient to the tangent at that point. So anytime we're asked about a gradient, you want the gradient function, and, well, you can sub in the point quite easily then. The next bit, determine the equation of the tangent to the curve, y equals e to the neg x, at the point where x equals 1. So if we look back to that picture, again stressing that this is not a e to the neg x graph, but you can see the tangent is a straight line. A tangent has an equation of y equals mx plus c because it's a straight line. So y equals mx plus c. And we already know that, well, the gradient is, what was it? Negative 1 on e. So m equals negative 1 on e, y equals negative 1 on e x plus c. And, well, now we just need c. And as you know, we just need to sub in a point in order to find that. And the point has to be where x equals 1. So step 2 would say when x equals 1, y equals, well, that's what we need to find. So remember, this is y and x. It's not gradient and x. So we need to sub in the y value. And, well, we can find the y value. I've just put x into the y equation there. So y equals 1 over e. So our point is 1 and 1 over e. And, well, let's sub that in. I'll just do it here. So y equals m, x, which is 1, plus c. And, well, 1 over e equals negative 1 over e plus c. We're adding 1 over e on both sides. So c must equal 2 over e. So now we've got the c value, we can state the equation line. Y equals m, which is negative 1 over e, x plus c, 2 over e. And that's our equation for the tangent. So that's the equation of the tangent which passes through that curve. So now that we've got the equation of the tangent, the next part is just asking us for the equation of the line perpendicular to the tangent. So if I go back to that representative diagram, again, it's not the actual diagram. We're not asked to draw an actual diagram, and, well, that curve is certainly not e equals e to the neg x, but it represents it quite nicely, and this is our line perpendicular to the tangent. So this line perpendicular to tangent is also y equals mx plus c. It's a straight line. We also know that perpendicular lines have the opposite gradient. They meet at right angles, and furthermore they pass through the same point. So this point which we already found, which was 1 and 1 over e, so 1 comma 1 over e for your x and y value is a point on the perpendicular line, and the gradient of the perpendicular line is the opposite to the tangent. So let's use that information. So perpendicular, and we could call that the normal. Well, the equation is y equals mx plus c, and the gradient of the normal is going to be the opposite of the gradient we've got here. So when we do the opposite gradient, we can do m1, m2 equals neg1. So we'd go neg1 over e times m equals neg1, and you can solve it that way. But I think much easier is to just say, well, let's go the opposite. Neg1 over e, we change the sign, so it becomes a positive, and we flip it. So that means it's just e. So the gradient is e. So y equals ex plus c. So we've done the gradient, and of course we just need to sub in the point. And remember, the point is still the same. So look back at that picture, and we see they both pass through the point 1 and 1 over e. So 1 over e, I'm going to sub that in, 1 over e equals e. Okay, and then 1 over e equals e plus c, and then, well, I can do c equals 1 over e minus e. And I mean, you could do a common denominator there if you wanted. If you did, you would have e squared and, over e, what am I doing? And then you'd have 1 minus e squared. So you could do like that if you wanted. I'm not sure what they're going to put in the book, but either way is fine. So either this for c or this, and our final equation would be y equals e x plus c. And so it could be that, or it could be y equals ex plus 1 minus e squared on e, which I think actually this one is probably nicer, because if we're going to do this one, you'd probably want to make a common denominator for everything. So I'm gonna go with this one here. I reckon that's probably the nicer one. Neither one is wrong, just maybe that's a nicer example, nicer solution. All right, and that completes all the worked examples from 5.3.